it shares a prefix with some other key. For example, ABAC, ABAC and ABC both have this a common prefix of AB, but one key is not completely present in the other. Uh, you can also say in a different way, like if you take the example of ABC and AB, AB is an example of case 3, but if we try to delete ABC, it is a example of case 4. So what should we do in each of these cases? In the first case, the key is unique for all prefixes. So here it does not coincide with any other prefixes. So what should we do? We can just delete all the nodes. Here CAB does not share its prefix with any other key. So if we delete CAB from the tree, this entire block gets deleted. So there is no use of keeping these nodes. So we will delete all these three nodes. Number three key may itself be a prefix of some other key. So let's say take the example of AB and ABC. So we cannot delete AB because if we delete, then this thing becomes loose and the tree becomes meaningless. So since it forms a prefix, we will just uh, uh, make these nodes like the end characters node which holds is end word. So if we try to remember the node structure, it has children, tree node star, children, and some boolean is end. So is end here signifies that some word has ended at that node. So we will just make it false over here. If you make it false, that there is no word ending here and that node is deleted. So now, then the fourth case, this is a bit tricky. Key may share some prefix, for example, ABC and ABAC. So if we try to um, delete ABAC, suppose, okay. So this thing AB is a shared prefix and we cannot delete that. So what we will do is we will check the largest prefix that is common to it, which is here ABC and ABC both shares the same prefix of two characters, and we will delete all the nodes starting from the next character, that is A and C. So if we delete these two nodes, then this word will be deleted from the tree. So these are the four cases. And if we see the coding of this part, the entire removal part, we will do it in a recursive way. So before that, I have discussed the four cases. Is there any question? Is there any question, or I shall jump to the coding part of this one? Mm, I guess no. So let's go back to the coding part. Okay, so let us define a function which will be returning. Okay, first let's say the name of the function is remove. It takes three parameters. Obviously, the parameters one of would be the current node. Let's define it as the root itself, which is the current node we will be working on. Then the key which we want to delete, and then one integer uh, um, variable, we will say it as index or ind. The default value, let's say it is 0. So what does index mean? So when we are checking for the presence of the key, uh, index defines the character from the start of the key which we are currently checking, and this will return a tree node itself. So it is tree node star. So first is the base condition. If we come to a node which does not exist itself, we will return null. Now, for now, there can be several cases. Firstly, we have reached the end of the key. That means we have checked the entire key. As I said, the first condition will be checked automatically within here. So here comes the fun thing. So if we have already reached the end of the key, that is ind is equals to um, length of the key. That means we have already checked all the characters in the key, and we are sure that it is present there. So what are the things that we will check now? If ind equals to len of key. So we will first and foremost check. First and foremost, uh, make that nodes is end here false, because whether we delete the node or not, this thing becomes the first primary task that we will do. So if root dot is end, root dot is end equals to false. So now here comes one thing. During the entire creation searching of the tree part, we have considered that all the nodes are unique. But if there exists two words with two exactly same words, then we can not just make root dot is end equals to false. So instead of that, if we can make it as an integer, and we can do this root dot is end minus equals to 1. This will just reduce the number of words ending at that point. So this is one case which you can do depending upon the question. Now the fun part. So this word has already been ended there, and if there are no children of that word, means that no, it does not. This comes as the third case, right? So if it has some children, this current node root has some children, then there is quite obviously some other key which is present, whose prefix is this word key. So if there is no sound, we can let's say we have a function, another function say is empty, which will check that all the 26 nodes of this 26 children are present, any of the 26 children is present or not. So if is empty root, which means if this will return true if there are no children of this thing, which signifies that there are no larger string whose prefix is this smaller key. So we can just delete the root, and root equals to null. And since we have checked the entire key, there is no point in checking the next children of this thing, because the key has ended there. So we will just return from here. So this ends the if part of this one, if part of this one. So now the other part comes, that this node is not the ending node of this key, means the key is not being consumed, the index is not equals to len of key. And now what should we do? Just a moment. Okay, so start after that, I come here. So this if part has ended, and it is having a return node, so there is no point in giving an else statement, we can directly write here. So let's so index here is the current position of the character we are checking. So we will check in this node actually. So if we get index, we will now we now want to get the corresponding array index for that index, I mean the children part. So index is equals to key of ind. This gives the character. So if we subtract a, we get the corresponding array position. So now we will just go on in a recursive way. We will go and check all the nodes, uh, all the subsequent nodes starting from that children, and see if the key exists or not. We will just go in a recursive way, simple recursion. So, and obviously this root, we are returning this root here once we have finished. So root dot children of this index. So if the current index is say current character is say c, so index will be 0 1 2, so it will be 2. So children of index will point towards essentially c in a array type way, equals to this will get in a recursive way the next part. So remove the current node that we will be checking is the next one only, root dot children of index. This is the current node. Then the key remains same, and now the index is becomes the next one, because we have already checked ind, so it becomes ind plus 1. So this becomes this key. We have got this part. And now there can be a condition as in the second case, that the key is completely unique, or maybe even the fourth case, where it shares a prefix and we have to delete some nodes. So at this position, once we get the root's children of at position index, we will again check whether this root has any children or not, according to the second or the fourth case. So again, we will check if root, if is empty root, this returns true when there is no children. And another part, this is empty root can also return true when it does not have any children. So there can be two cases. Firstly, that we have deleted some of its children because it becomes it is, say, a unique. For example, in case B, uh, just give you an example. So CAB, if we are currently at position A over here, we have already deleted B. So we are at A, and there is no children, so we will delete this node and this will return true. But this will also return true if we are deleting A, B, A, C, and we are currently at position B. If we are currently at position B while deleting A, B, A, C, we have deleted the nodes A and C, and we are currently at the node um, B, and it does not have any children, so this will return true. But it is a common prefix to A, B, and ABC, so we cannot delete this node. So how can we be sure whether this node is not a part of some prefix or not? Very simple. We will check whether it is an ending node or not. um, mm, so yeah. Yeah. So root dot is end equals to false, then we will delete the root. And we will make root equals to null, and then we will return root. So this takes care of all the possible cases. um, and one thing I would just say, based on this year's trends, this tree part was very common in Google's interview questions for both internships and FTs. So it will be better if you study this part easily for your batches, interviews, and stuff. Okay, so any questions? Anish, are you there?
Yes, hello.
Okay, so if there are no questions, we can move to the next part, which is the binary tree, I think.
Also, we have a easier method for deletion using a count. So, let's say if we maintain an extra parameter for every node. So, wait, let me share this. So, is the screen visible? Yeah. So, let's say for deletion and insertion, we can use the same method if we use a extra parameter called count. Okay. So we have the as usual we have this, and we have extra parameter called count. Okay. So these are the two data structure, means what should I say, means uh, objects or parameters that we are having inside the try object. So we initialize a try object using these two parameters. So, so basically, children means the children of the current node, as we know, and count is the number of values or the number of nodes that are currently present for the current node. Okay. So for insertion, what we can do is that, like def insert, we have, let's say we have to insert a particular string. So we start iterating from the root, and we start iterating through the string. Okay, so we first find out the ASCII value of the ith in ASCII value of the ith character of s. So ASCII value is equals to uh, ORD SI minus 65 or 97 according to uppercase or lowercase, and then we check that if till self dot car dot children ASCII value equal none. So if the current children is empty, we create a new child in that place. So self dot car dot children ASCII value is equals to a new node, that is trie. Otherwise we go and we change the current node to that children. So we update card as self dot card equals to self dot card dot children as given. Okay, so now what we do is that since we are inserting another value in this current object, we increase the count of this object by one. Okay, now is this part clear why we are increasing? Because we are inserting one more value here for this current object. Okay, so like this you can insert, and for deletion you just have to do one more thing. Like all of this will be same, but instead of incrementing you just subtract or decrement. So this will be your deletion. And you have to check one more condition is that if self dot this one is none, or so either the children that we are looking to have is empty, or it has a count of 0. So basically these two things are same. If a object has a count 0, so let's say we are looking for an object A. So if A dot count is 0, and if A is null, so these both things are basically meaning the same here. Okay, so for making things easier, we are using the count here, because for deletion, what Shaunak told was very complex. Like you have to check a whole number of things. So like why focus on so much of things? Like you can just keep a count that how many times we have inserted in this node, and for deletion we can just subtract those time, means every time we delete a thing we will subtract one from that node, and every time we insert we will increase the count for that object by one. So it's basically like that. Okay, so for that's why you have to check an extra condition is that uh, if the current node has a count 0 or not. If it has a count 0, so that means that it has been inserted x times and has been deleted x times. So like it's not anymore present. So like that. So is this method clear? Hello. So any questions?
Yes,
Means any questions on this deletion method? And you can do search also using the same thing. So let's say you are searching for this, so all will be same. So just here you check that if it is none, Or let's say if its count is 0, you return false. Otherwise you go on and you don't do means you don't update count because you are searching, right? You are not inserting or deleting, so you don't update or decrement count. So count is as it is, means count remains as it is. So you just check that whether the node means the current alphabet or the current character is present, means the object for the current character is present, and it has a count of greater than 0. So but so if it is not present or the count is 0, you return false. Otherwise at the end you return true. So is this part clear? Like this is like a shortcut method, like not the what should I say, like not the original method. Like if anyone asks you to delete, you should do what Sonak told, but this is like the shortcut or a tricky method, like you can do very quickly if you need. So any questions, or we can move to the binary try part. Okay, I guess like we don't have questions, so we can move to the binary try. So like the original try, so in the original try we consider that the our node can have 26 children because there are 26 alphabets. But for the binary try we have only two children. Okay, so like every node can either have one or zero, so two children. Okay, so things are very much same, things are very much easier also than the general try. So the class of binary try is defined as like this. We have three things. So those who don't know, this is the constructor class in Python. Okay, so we have three things here. One is the data which we take. Okay, so data is basically the number which we will store, and the left child which we initialize as empty.
Hello, Onyx, just do it in C++ or just a yeah, prototype. Don't use Python.
Okay, okay, okay. So like I am writing the pseudocode. Okay, so like so the binary try has these three things. So the so it has three parameters. So like it will have a data, it will have a left child which will be empty or null, and it will have a right child which will be again null. Okay, so like let me tell you how it happens once. So like let's say you are inserting a number. So let's say you are given the number x equals to let's say 30. Okay, so its binary representation will be 1 1 1 1 0, right? So 4, sorry, 2 plus 4 6 14. Yeah, it is a binary representation. So we have a root, and then we take the first byte which is 1. So we go 1. Just wait 1 second. Yeah, so is the paint visible? Hello.
Yes.
So as I was telling that 15 has a 1 1 1 1 0 binary, right? So in binary trie, we have a root, just like the normal trie. Like binary trie is a simplified version of trie. Okay, so it's a more easy and a less complex version of a generic trie. So since we have one here, we take left is for 0 and right is for 1. Okay, so we one here, so we go to the right one. So we have this node. Again we have one. Again we have one. So we have one, 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 then again one, and then 0. So these are the nodes that we will create on the process of inserting 30. Okay, so this node will have a data of 30. Okay, so this node will have data equals to 30. Okay, so we first create a root, and then we go on creating the nodes as we have. Now let's, after inserting 30, we insert 15. Okay, so 15 has 1 1 1 1, again 0. Because we have to insert the same number of means bytes or something. So first we take 0, then 1 1 1, and again 1. Okay, so this node will have a data of 15. Okay, so now let's say after 15 we insert let's say 16. Okay, so 16, not 16, let's say we insert 31. Okay, so 31 will have 5 ones. Okay, so now when we start from root, we already have a 1. So we go to the next one, we also have a 1. So next one 1. So 4 ones we already have, this 4 ones. And then after this we again add another right child of this node, and we have 1 here. So now this node will have data 31. Okay, so is it understood that how it is working? Hello.
Yeah, yes.
So now let's go on to the coding part. Just as I told that it has three things: data, left, and right. Okay, so now let's say we are in the function insert. We take the we first make a root. Okay, so root is an empty object with let's say the without any data, or we can store 0, because 0 has nothing. So we initialize a root, and then we and write a function for insertion. So let's say we will insert the number x. Okay, and we let's say the x has a maximum of 30 bytes. Okay, so x has maximum 30 bytes, or let's say x varies from 1 to 2 to the power 30. Okay, so this means that x will have maximum 30 bits. So for I in range 30 to, sorry, for I 30 to 0, we first check that whether the ith bit is 1 or 0. So for that we check that if I and 1, sorry, not I, x is 1 or not. If it is 1, So everyone knows now what this thing does, or I have to explain that what it is doing. Hello, hello.
Yeah, I know. Yeah.
Like everyone knows now, like what it is doing. This part, the highlighted one. Okay, like Neeraj knows. Okay, I am assuming that you know. Okay, so basically it checks that whether the ith bit of x is one or zero. Okay, so if it's one, just as I told that the right child is for one and left child is for zero. So we check that whether we have a right child or not. So if also we take car as root. Okay. So we check that whether if car dot right is empty or null. If it's null, we create a new object. So car right equals to bin try 0. Okay. So bin try 0, and we update car to car dot right. Okay. Otherwise, if the bit is 0, we check similarly for the left one. And after we are done, just as I told that the last, here see the last node every time has the data of x, right? Here the last node has data 30, and here the last node has a data 31. So the last node will contain the number, means the data of the last node will contain the number. So car dot data will be x at last, means the last one. Okay, so like this you have inserted. Now for searching a number, like if if you have to check that whether the number is present or not, so function, uh, let's say search x, everything is same. So you uh, copy this, like the things are same. Just if the if it's null, you don't create, because if the right child is none and the bit is set, then it means that there is no such number, right? So you directly return false. Similarly for this one, if the ith bit is 0 and the left child is null, so that means that suggests that there has been no number inserted with the ith bit 0, right? So return false. And the at the last check that whether if card dot data equal x, then return true, otherwise return false. Now is this clear? So this you are checking because you have to check like this, that if the last if the data of the last node is 30 or not. So for example, if you are checking for 30, so the data of this node will be 30, right? So you are going from this one, you are going here till here. So all the nodes are present, and you also have to check that whether the data of the last uh, whether the data of the last node is 30 or not, right? Because uh, even even some number like 60 will also have all these nodes, right? What is the uh, binary one of 60? It will be same as 30 with an extra 0 at the end. So 30 will also have four ones, then followed by a 0, and then again after this 0 it will have a 0. Okay, so 60 will also have this structure, but 60 will not have data equals to 30 for this node. So 30 will be stored as the data of this node only when 30 is inserted. So for that reason, we are checking that the current node has a data of X or not. If it has, then we return true, otherwise not. So till this, it's clear or not. Don't know much about sets DS, like where we have used set here. We have not used set anywhere.
Nana, I asked a question, different question.
Oh, oh, so is this clear or like do you have any question? If you don't have any question, like you can go and solve this problem, like find the maximum XOR between two elements in the array in O of n log n. Okay. Like you can choose any two elements from the array, and the XOR of those two elements that you have chosen should be maximum among all such combinations. Okay. This is the means basic question of binary trie. So this should be solvable by you. Like it's also a very common question for online assessment and all. Like for my hacker rank online assessment, this question came. Also there is it can be XOR, like do three things, like find one is find the maximum XOR. Second one, you can find maximum OR. And the third one, you can find not OR, like well, like let's find the maximum XOR only. Okay, because other things will be a bit tough. So find the maximum XOR between two elements in an array using, means in the complexity of n log n. And space complexity should also be n log n, means both time and space should be n log n. Like this is also a very popular question. You can, if you search, you can get in GFG the solution if you can't solve on your own. So there also you will see that they have used try. So same thing for that. So any questions like on this? So like we can end, like we have a contest from 7, so you will get a break of some time. So if you don't have any questions, you can start leaving.
Okay, thank you, Bhaiya.
Yeah, thank you.
Thank you, Bhaia.